Hello, this is MSUM's final presentation report for the Drone Club. I'm Jacob Carson. I was the pilot and part engineer.
And I'm Alex Nemi. I was the main programmer and the person in charge of most of the sensors.
I'm Lucas Clark Burnett. I was the data analyst, and our other data analyst, Hiro Suzuki, couldn't make it.
The flight plan actually went down the day of. We used laser plate in a vertical configuration to look down, just to get see everything from a down or from a top view. This allowed us to see anything that was hidden behind a wall or on top of a tower. The second thing we did, we had the laser plate in a horizontal configuration to size objects, to give them height, and this also allowed us to look on the side of the tower and the back side of the wall. The third step, we used the sensors to scan points of interest that we found with the cameras. This included magnetism and heat. And lastly, for the sake of the safety of our drone, we first collected the liquid sample with a sponge, and the second collected a dry sample with a scoop. The laser plate configuration, like I said, we started with the camera in a horizontal or a vertical orientation to get the X and Z coordinates. This allowed us to see on top of the tower and see what was inside the bucket. Next, we flipped the camera and the lasers to the horizontal configuration to get sizes, the height, in the Y direction. After we were done with this part, we turned the plate 180 degrees so we could go onto the back side of the wall and see what was there and not make the pilot job myself. It just made it easier for me to fly the drone and not have a mirrored operation.
So for our sensors, we decided to go with a Arduino Nano 33 BLE as our main sensor package because it included most of these sensors that we needed, like a accelerometer, magnetic field sensor, barometric pressure, and gyroscope. It had more, but we didn't use those. That was then connected to an SD card reader to then save all of our data. And then we also had a non-contact infrared temperature sensor, and that measured both infrared temperature at about a 90-degree field of view. It also measured the ambient temperature internally inside the temperature sensor, and that was mounted on a aluminum rod to make it so we could bend it to make it face forward or face down. For our solid sample collecting, we used a 3D printed part that was then glued to a piece of PETG plastic that was bent in such a way that you couldn't easily tip the drone over and wedge yourself into the actual solid sample. It would kind of slide along the top. And we use that to then scoop up about a milliliter of our dry sample.
For the liquid, we quite literally used a sponge attached to a copper wire that was hooked onto the drone. This was far easier than using the scoop. We discovered in the walkthrough that the first prototype of the scoop was not ideal for collecting liquid, so this just made it easier for the pilot's job, and it was easier. The sponge, it was very effective. One little dunk, and it had plenty of liquid for us.
So here's what I managed to determine about our liquid sample and our solid sample. So first with the liquid sample, I took a small quantity of this, approximately 1/20 of a milliliter or 1 drop, and tested the refractive index of it using a refractometer like this. Here's a measurement of the specific gravity. Here's another measurement. This one is of pure deionized water. As you can see, the specific gravity of the sample that we have is slightly higher than that of deionized water. I assume that there is some level of ions in the solution that increase that level, most likely just some salt. I then took another 1/20 of a milliliter or 1 drop and dissolved regular table salt into that single drop. And then I tested the refractive index again using that same piece of equipment. The light refracted so far inside of the refractometer that it no longer showed up on this. So that implies that the specific gravity is over 1.07, which indicates that it dissolved a lot of the salt. The only things that can dissolve salts are polar solvents because it's an ionic compound. So our liquid has to be some polar solvent. Most likely it would have to be water because of how polar it is. It could theoretically be something else, but that seems unlikely because it doesn't have a smell or anything that would indicate that it's anything other than water. One of the first things that we noticed with the solid sample is that it is very magnetic. So the first thing that I did is I used a magnet to actually separate the magnetic parts from the non-magnetic parts. It looked to be a combination of a black metallic compound that is magnetic and a mixture of sand gravel type material. So we're unsure of the exact compound of the metallic material. We believe the compound is magnetite because it's a fairly common compound and it is magnetic.
Here's the lay of the land, the lay of the area, the fly zone, whatever you want to call it. There are the dimensions. I'm not going to read them off. Some special items that we found in the area, or unique items, I should say. The deck of cards, or what we believe was a deck of cards inside the bucket on top of the tower. The buckets, the envelopes were all the same sizes. The trash can, which was part of the tower, and the table that was holding the tower. Something to note, the bigger the object, the bigger the error. Typically, when we were dimensioning the whole zone, the error was pretty high because we had to frame it in steps, and that just raised the error by a lot. What was inside the bucket, like I said, it was about the size of a deck of cards, so we could only assume that it was a deck of cards. The dimensions were 6.5 by 9.5 centimeters with a plus or minus of 0.2 centimeters.
So for our sensor data, I'm going to go from left to right. First, we went over package 3, and as you can see, there was no remarkable magnetic or temperature data. But when we got to package 2, you see fluctuations in temperature and magnetism. These fluctuations ranged to about 27 degrees Celsius and then 65 microtesla. And then for package 1, you don't see any magnetic fluctuations, but we do have a temperature fluctuation of 24 degrees Celsius, which is 1.5 degrees higher than our baseline of 22.5. Then we go over package 2 again, and this just verifies that we have both temperature and magnetism. And then the cold spike that you can see is the liquid sample. There's no magnetism present, and the same is true for the solid sample. There is no magnetism present, but they're both cold. And this is from the photo on the back side of the wall. We're able to read 4 lines clearly, but there may be 5. It's just hard to tell due to the high exposure of the fluorescent lights. But yeah, that's that. The pictures, they were 22 by 28 centimeters, which is roughly the size of regular letter-sized paper from a printer. But our resolution wasn't very good, so we couldn't really make out anything specific other than the fact that they look like pictures of satellite terrain, maybe of Mars or something.
Things we learned over the challenge. Time management is very important, obviously, in these kinds of things. Second, flying the drone took practice, which there was a lot of, but we learned a lot while we were practicing. Every time we swapped the batteries, we had to re-tear the controls because our drone had a tendency to drift back into the left. This made piloting tricky, especially if you add weight, because the blue heron becomes more finicky the more weight there is. Things we could do better next time if we were to do this again. Trying to reduce error in the scaling videos. This is talking about the laser configuration. The error could have clearly got bigger as the objects got bigger. This just made it harder for us. They could have been more parallel. Plan projects out more. Basically, time management was not the best for us, but if we planned out our projects, it probably would have been done a little better. But and weight managing, this kind of ties in with the whole tearing and the drone being finicky with more weight added.
So we are the MSUM Quadcopter team. We'd like to give a big thanks to the Minnesota Space Grant Consortium, our faculty advisor, Dr. Lindos, the panel of judges, Dr. Thelma Burkwo, Ben Bogart, and Dr. James Flatten.